I'm not saying much about the prediction models themselves. I just briefly mentioned that there is predictability in the El Nino business, which was what was exploited by Mark Kane and Steve Zebiak in the 1980s to build that simple model. And they just decided that the relation between the thermocline movement and sea surface temperatures in the east and the resulting east-west SST gradient and wind anomalies can be used to, develop a simple, very simple model for sustained oscillations. And they even went ahead and made a successful predictions. Since then, it's been a battle of wills in terms of which models, which class of models will do better predictions. Better is a word that can be used in many ways because El Ninos have these evolution phases, onset, growth, mature phase, decay, etc. You can focus on a few things, but nonetheless, we know that there are stochastic forcings involved, which raises questions about predictability as a whole versus individual events where maybe the stochastic events like westerly wind bursts are missing even if discharge happened and so on and so forth. So 2014 is a good example. Here is 2014 evolution of the Nino 3.4. You can see that it got warm but didn't quite qualify as an El Nino, even though some people call it mild El Nino. But 2015, of course, ended up being a fairly strong El Nino and then died away. Now we almost forget about it, but because 23, 24 came and now 26 is making so much news. So you can see that the forecasts were calling for a stronger El Nino in 2014, but it died away for whatever reason. And if you look at the statistical models, they also did something similar. And this battle of the models and the beauty contests also keep arguing about whether statistical models can really do better than dynamic models and whether simple models like Kane-Zibiak or other linear prediction models can do better than the full global climate models. And we don't have enough samples, but in general, so far statistical models are basically keeping up with the dynamic models. Given enough information, they seem to evolve. Similarly, the idea was that the statistical properties of El Ninos change, so using past events to build a statistical model can fail in a changing climate, and this was the case for monsoon predictions as well. In fact, monsoon statistical predictions basically never had any skill at all, but it was still used for a while. So if you can look at the, I've put the, yeah, I'll come back to that a little bit later on. So this idea of whether statistical models can beat the dynamical models continues, but when you look at forecasts from a center like the International Research Institute and NOAA's Center for Climate Prediction, etc., you can get lots of models listed along with statistical models as well, because nobody wants to throw out the statistical models quite yet. So basically the answer is right now, dynamical models do just about as well as statistical models, or to say it better, statistical models are doing just about as well as dynamic models, which probably means that dynamic models are not capturing some of the stochastic forcing from the westerly wind bursts, even though they are there in the reanalysis products as we saw before. We saw that these are from reanalysis products era, 10-meter winds, 10-meter height. So you can see that they do capture the events, westerly wind burst events, which happen on short 7-day time scales, basically synoptic time scales, weather time scales. So if you look at the predicted Nino 3.4 index and observed Nino 3.4 index from one of the products called optimally interpolated SST, you can look at various time scales. Dynamical average at lead 0, which means basically near real-time prediction. El Nino is already in place and you're just making a prediction, let's say starting on December 1st or so, and the correlation between predicted and observed is 0.96. So models are basically almost perfect because already El Nino is in place, subsurface information is available, dynamic models initiate the ocean and integrate forward, and boom, they produce the El Nino. It doesn't say much about the necessarily the amplitude. It's just the phases of Nino 3 between the observed and model are perfectly matched, and the statistical models at least 0, also 0.93 correlation, not bad at all, right? And this is going from 2002 to 2016, so however many events there are. And this is the dynamical models with lead 4-month lead. So you're now back into the end of the summer into fall months. The correlation drops, longer the lead, lower the correlation as expected. And correlation is with the El Nino DJF. So you can see that the correlation drops to 0.8, and statistical average for statistical models produce slightly lower correlation at 0.7, but the 0.7 skill score is considered really good. If you go to 8 months, then the dynamical models drop to 0.55, but then the statistical models crash to 0.36, which is basically not usable. Anything below 0.5 you would hesitate to use. So maybe dynamical models, because of their ability to represent ocean, atmosphere, land interactions, ocean memory, atmospheric response, Birknes feedbacks, etc., explicitly, their skill really is useful when you want to do long-term, long lead forecasts. So 2026 forecast from January, February was solid. They have remained solid. So statistical models cannot be trusted for such long lead times. So there you go. The dynamical models are useful because this really helps plan things as well. Governments begin to make decisions based on El Nino forecasts. India banned sugar export, increased the edible oil import tax, and previously 23 it had banned rice export. Banks make decisions, fishermen make decisions, governments make decisions, people make decisions about, if you're from a region that gets hit with droughts during an El Nino, like Nordeste of Brazil, which is famous for migration of people, I think migration in or out, but governments demand, local government may demand funds from the central government saying we are having labor problems or drought issues for agriculture and so on and so forth before the El Nino even appears. Okay, so those are the kind of things. Artificial intelligence, this is an article from 2019 from Science. Artificial intelligence could predict El Nino up to 18 months in advance. Program could help threatened communities better prepare for disasters. There are also similar claims from dynamic models, but when you look at actual predictions, even when they are before the spring, we talk about the spring barrier. We said the gradient in the tropical Pacific is flat, system is noisy, very vulnerable to noise. Hence, there is spring barrier that we cannot test, but we claim 18 months in advance a prediction can be made, and this may be true for strong El Ninos like 82, 83, 97, 98, 15, 16, and maybe 26 will also emerge as a strong El Nino. And that if you look at the overall skill, then maybe the high skill score basically depends on a few big El Ninos which were better predicted. So we'll come back and look at in the next podcast as to whether there is additional information that we can use to make the long lead forecasts more skillful, more reliable in some ways. So can we take this 0.55 at 8 months to something higher, 0.8 or 0.9 or whatever, right? So that is possible theoretically, predictability wise, but we'll come back and look at that because that's going to depend on the lead time of the recharge discharge. We already said that the discharge starts as the meridional tilt of the thermocline and then turns into zonal tilt, and that the meridional tilt leads the zonal tilt by up to 18 months. And we said the discharge also starts the previous summer. So we'll look at that again and see if there is a way to use that information if Anyway, let's come back and do that discussion separately instead of going into it right now. Okay, see you.